So thank you everyone for coming to Zhong Lu's thesis seminar. So Zhong Lu has been here since 2009 as part of the APP program. And so it didn't take me very long to work out how clever he was. He started getting very high marks in all these exams. And actually you might have to edit this bit, Rob. So whenever I wanted to check my model answers for an exam, I always used to go and find Zhong Lu's paper and compare. And if there were any differences, most times he was right and I was wrong. There was one time it was not that case. But he did his fourth year thesis looking at Anodic Aluminium Oxide, and he was awarded the University Medal and has been studying here with an IPRS for the last 3.5 years. So he's in the process of writing up his thesis, and today he's going to talk about some of his thesis work, which is Anodic Aluminium Oxide for passivation in silicon solar cells. Thank you.
Thank you, Alison. Thanks everyone for coming. So today my topic is on the use of aluminium oxide, anodic aluminium oxide, for solar cell passivation. And here's the outline of today's presentation. So I will briefly give an overview of my objective and the research area about my project, and then I'll focus on a method that we developed to manipulate the stored charge in AO, and then talk about some application of this AO in this passivation. Alright, so the objective of my project is trying to integrate the AO structure into a solar cell design in order to achieve both localized contact and an enhanced passivation. And here's the research area. So I start off with some investigation on how to achieve the localized contact, use the AO as a self-patterned template, and we managed to achieve a good localized contact with low contact resistance, but it also come across some issues, and that brought us to my next research area, where I'm looking at the possibility of manipulate the stored charge in AO. And yes, I was lucky to be able to control the charge in AO, so I spent some time looking at the mechanism of this manipulation, and finally trying to use this charged manipulating scheme into the solar cell passivation. Right, so let's talk about this technique. So first of all, I would like to talk about why it is valuable to be able to change the stored charge in a dielectric. So when you are looking at surface passivation, there are two important aspects. One is the chemical passivation, the other one is the field effect passivation. And the chemical passivation is mainly to deactivate the surface defects or the recombination centers at the surface. And people have been using silicon dioxide, silicon nitride, aluminium oxide, all sort of dielectrics to do that. And the other aspect is field effect passivation. So namely, is actually achieved by inducing an electric field in the semiconductor by this stored charge, which I denote here as QEFF, so effective stored charge, which will induce an electric field that can change the carrier density at the surface, and so that we can achieve passivation. And here are some examples where different stored charge can make a difference, big difference in the surface passivation. So in figure A, we are having a conventional, not conventional, a very typical N-type substrate and a P-boron diffused surface. So to passivate this structure, it is preferable to have a negative stored charge. Reason being that with a negative stored charge, you will be able to repel the minority carrier, which in this case is electron, away from the highly recombinating surface. So if, on the other hand, you are using a positive charge, it can cause a problem because it's attracting the minority carrier to the surface, and the surface is highly recombinating. So it will instead of reduce the surface recombination velocity, it may even increase it. And for the other case where we are passivating the N-type surface, it's good to have a positive store charge. And that's one of the reasons why people are using silicon nitride when they are passivate the phosphorus emitter, and using aluminum oxide to passivate the P-type surface. But if we are having a structure like this, interdigitated P and N, then what's the polarity? Well, I don't have an answer here, but to be safe, it is better to have a low store charge or even a neutral store charge. So we don't have a very good field effect passivation, but if you can manage to get a very good chemical passivation, they still have a very strong surface passivation using this scheme. Yep, so you can see that the charge can have strong impact on the passivation, surface passivation, depending on what type of surface doping you're having. And another important aspect about the store charge is when you come to fabricate a localized contact. So the example showing here is when you are having a localized contact through silicon nitride and contacting the P-type substrate. This is a very typical structure. So the problem is that the silicon nitride stores a positive charge, which is the same as the AO, and it will attract the minority carrier to the surface just underneath the dielectric. And there is an inversion layer, and this inversion layer would act as a shunting path for the minority carrier, so it would reduces the device voltage, so it's really bad. And as I mentioned before, part of my PhD work is trying to develop something like this, so a localized contacting scheme using AO. And yeah, we managed to do that with the AO, the self-patterning AO. So here's two SEM images showing verifying the localized contact. So we have a silicon that is metallized with the AO structure, and the AO is removed, and the metal is removed, and then the silicon is etched in a P+ selective etching solution. So the groove you see here is where the localized BSF is. So you can see that we demonstrate a localized contacting network along the textured pyramid boundaries. And this is a cross-section SEM showing the thickness of this BSF. So it's around 1 to 2 micron. So the contact resistance is really good and it's quite reliable, but we're having a problem with the device voltage. So as we see here, the PL image of the sample before and after metallization, you can see a significant drop in the voltage. And to explain this problem, a PC2D model is built to quantify the relationship between the BSF thickness as well as the contact spacing on the VOC. So we can see from this simulation that if you have a very thick BSF, you don't have the penalty of losing the VOC when you are closely spaced, closely placed your contacts, localized contact together. But if you have a very shallow BSF, this is going to hurt the VOC, and that's what we are seeing here. So the contact spacing in my case is only 2 micron, so it will be somewhere here. So if I'm having a very shallow BSF, it would effectively as the same as the full contact, which is has a very low voltage. But in my case, I don't have the benefit of a full aluminum contact where you have a very thick BSF to shield the minority carrier. And I also don't get the benefit from localized contact where you have the passivated area that is low recombinating. So another aspect that makes this situation worse is the store charge in the AO, which happens to be positive. And that, as I explained, would introduce parasitic shunting. So that's the motivation why I moved to explored the possibility about trying to manipulate the store charge in AO. And here, let's see how I can do that. So this is the setup that I used to grow the anodic aluminium oxide. It's quite typical. The only difference is this unit, which is a potential stat. It has a function to generate a programmable current waveform. For example, this is the one that I used. So I use pulse anodization to grow the AO. So typically people would use a constant current or constant voltage power source to anodize aluminium to grow AO. But in my case, I try to use a pulse current which has both positive and negative cycles. And the only thing that I change in my process is the ratio between the positive duration and the cycle length. So I have demonstrated that by changing this ratio, you'll be able to change the store charge. And this is the test structure that I used for characterization. So I start with a porous P-type substrate, and then I grow a very thin silicon dioxide, and then I put aluminum on top, and then use this setup to grow an AO. And then I fabricate a MIS structure and use the CV measurement to characterize the store charge as well as the interface defect. So let's look at the first result where I demonstrate the charge manipulation. So here is the positive cycle percentage. So 100% means that you are using a constant positive current for anodization. And as you reduce the positive cycle percentage, you are increasing the more negative cycles. So it is shown that with decreasing positive cycle percentage, the effective store charge is reducing. And you can also see that with a thicker AO layer, you have a wider range where you can achieve. But looking at the minimum, the lowest store charge for different combinations, they're actually quite similar. So this is the zero store charge, neutral store charge. In this case, I can only manage to get a slightly negative store charge. And in my other experiment, I find that if you reduce this interlayer, the thickness of this interlayer, you would have a stronger impact. You can have a better or a more negative store charge that you can achieve. And the reason is that you can imagine that if you have a very thick silicon dioxide layer, whatever is happening in this AO will have a very limited impact on the band bending of the silicon dioxide. So if you are reducing this interlayer thickness, the charge in the AO would have a stronger impact on the silicon, so that you can have a wider manipulation range. Yep. Yeah, so it is shown that manipulation is possible, but in order to understand the mechanism, it is useful to try to investigate the distribution of this store charge. So a very commonly used method is to etch off the dielectric at different locations for different durations, so that you achieve a step profile. So this is a sample, an image of the sample. So you can see that there's a color difference that corresponds to AO with different thicknesses. And based on theory, the flat band voltage of this MOS structure can be given by this expression. And if you take a closer look, it's a function of the thickness of this layer. So here we propose a store charge model where you have a bulk store charge in the AO volume, and you have a fixed interface charge between the AO and the silicon dioxide. And then you have a fixed interface charge between the silicon dioxide and the silicon. And I assume that you have a constant charge. So the only variable here is the thickness of your dielectric. And since I have different thicknesses, you would be able to graph the flat band voltage as a function of the dielectric thickness. And here's what we are seeing here. This is flat band voltage. This is the effective AO thickness. And you can see that you have this kind of curve. It's a polynomial fitting. And based on the experimental data and this expression, you'll be able to extract each parameters that we proposed in our store charge model. So the key finding here is we have a negative fixed charge at the interface between AO and silicon dioxide, and a positive fixed charge at the interface between silicon dioxide and silicon. And we also have a bulk positive stored charge in the AO volume. So this too is actually quite consistent with what other people are finding regarding the aluminum oxide and silicon dioxide stacks. And with this in hand, you'll be able to predict the store charge as a function of different combination of dielectric stacks. And this is consistent with my finding where when you reduce the silicon dioxide interface, you can achieve a more negative store charge. So different lines correspond to different silicon dioxide thickness. And you can see that with only 3 nanometer silicon dioxide, you can get a more negative store charge. But with thicker layer, the range that you can manipulate is smaller. And here is the experimental measurement of a sample that I anodized with a 12 nanometer interlayer silicon dioxide. And you can see that it actually agreed quite well with the simulation. For field effect passivation induced by the store charge, the stability is always an issue. So people have found that store charge dissipate with time for most of the highly charged films. And this is also the case for my AO layer. So here I show 2 groups of the store charge. In figure A, you have an positive store charge, so this is all positive. And in figure B, you have negative, so negative store charge here. And you can see that for the positive store charge, you have a strong degrading of the magnitude in the first 6 months. So that's 200 days. And then it will saturate afterwards. So I've been monitoring this structure for over a year, for a year and a half. And for the negative ones, you can see that it's relatively stable for most of the samples. And the reason for this deterioration in the store charge is due to the oxygen deficiency that presented in the silicon in the AO. So as in my later section, I would discuss the origin of the positive store charge. And my conclusion is that it actually comes from the oxygen deficiency. And when I store my samples in the atmosphere, the AO film would absorb or incorporate the oxygen, which reduces the oxygen deficiency and reduce the positive store charge. But for the case of negative store charge showing here, the oxygen deficiency is not dominating, so you would see a much more stable behavior. It has been widely reported that annealing of dielectric would significantly impact both the store charge and the interface state. And it is also the case for my study. So I have used 2 groups of samples to test the impacts of annealing. So for this one, I have the aluminium capping the AO and then put this sample into annealing. For the other group, I anneal the sample with a bare dielectric. So the idea to put in this aluminium on top is to test the quality of aluminium annealing, which is also known as anneal. And the samples are annealed at 400 degrees for 30 minutes in 3 different type of gases. So the first one is the pure nitrogen. So you're only looking at the thermal effect. And the second one is the mixture of nitrogen and oxygen. So you are looking at the impacts of the oxygen. Third one is forming gas. You are looking at hydrogenation. So here's the CV curve before the nitrogen annealing. To give you a better idea, if the curve shifts towards the right, it means that you are reducing your positive charge. So if you are shift towards the left, you are increasing your positive stored charge. So as you can see here, after annealing, without the aluminum capping, so in this case, the curve almost overlapped, you have a slight change in the shape which corresponds to the change in the interface defect. But if you anneal the sample with the aluminum capping, you have a strong shift to the negative charge. And the reason being that with this capping, you would have the hydrogen passivation, which is the result of the reaction between the water molecule left in the AO, which reacts with the metal, the aluminium, and then release atomic hydrogen, which can passivate the interface defects between the silicon dioxide and the silicon. So you reduce the interface defects, and you also reduce the measured stored charge. So you can see this shift here. And for the annealing in nitrogen and oxygen mixture, one significant difference compared to the other one is the very strong shift to the right. So you reduce a lot of your positive stored charge. So this is the 0 voltage, and you can see that it shifts a lot from the initial value to here. And that's actually the most negative stored charge that I measured up till now. And we would have a more discussion about the reason why we have a strong shift after the oxygen annealing. In the forming gas, you also see this shift, which is probably due to the passivation of the interface defect. And here shows the interface defect density, the mid-gap DIT, after annealing for these two groups for different gas. And you can see that if you have an aluminum capping, generally you have a lower DIT due to the hydrogen passivation from the annealing. And you can see that the forming gas annealing is the most effective annealing in terms of reducing the interface defects, because it provides extra source of hydrogen from the gas. So as we can see, the annealing in the nitrogen and oxygen mixture would reduces the positive stored charge, and the question is why. So to explain for this question, I present here a research reported by a research group from Stanford University. So this work is done on the 3-5 semiconductor, and the dielectric is ALD aluminium oxide. So the author stressed that when you have an oxygen deficiency, you would have aluminum dangling bonds in the volume of the aluminium oxide. And if you look at this band alignment diagram, the aluminium dangling bonds is above the Fermi level of this structure, so it would be positively charged, which means that the aluminium dangling bonds would contribute to your positive bulk charge. And the aluminium dangling bond is contributed from the oxygen deficiency, which is quite straightforward to think about. So when you don't have enough oxygen, you have a lot of aluminum atoms that are not bonded to any oxygen, so they have the dangling bond and they are positive. And it would be similar in my case. So in order to test this assumption, I've done some XPS profiling of my samples. So here I shows the oxygen to aluminum ratio for my samples before and after annealing. And that's the depth profile. So here is 1.5. So if you have a oxygen aluminum ratio that is lower than 1.5, it means that you don't have enough oxygen, so you have oxygen deficiency. So on the other case, if you have this ratio above 1.5, you have aluminum deficiency. So as you can see here, before annealing, most of the aluminum in the volume of the AO has oxygen deficiency. And you can also notice this slope, and it's probably due to the voltage difference during my anodization. So according to literature, when you have a higher anodization voltage, you would have a higher oxygen content in your AO. And so this is a 400 nanometer AO, and it grows from the interface between the dielectric and the semiconductor. So it grows from here. So at the beginning, you have a lower voltage because the resistance is still low, but as the film grows, the resistance increases and the voltage drop across your AO film increases, which will increase the oxygen content in this film. So you will see this slope. And so after the annealing, you can see that we have a strong shift of this oxygen to aluminum ratio over the whole volume. So we increase the oxygen content and reduces the oxygen deficiency, and thus reduce the positive stock charge. And that's what we are seeing in the oxygen and nitrogen annealing. All right, we've talked enough about the stock charge, and let's discuss something about the passivation. So firstly, I'll show an example of AO passivating the N plus surface. So this is the test structure. We start with a P-type substrate and use phosphorus diffusion to grow an emitter, and then you fabricate AO on both surfaces. This is a symmetrical structure that are used to extract the surface recombination velocity, or J0. And you can see that before anodization, the J0 value is 85, the average, and after anodization, it reduced quite a lot, which means that you have an enhanced surface passivation on this type of structure. And the reason is that the AO stores a positive charge and is preferable for passivating an N plus surface. And if you look at the lifetime data, you have a lifetime enhancement over the entire injection level. But if we look at the other case where we're trying to passivate the boron emitter, we're seeing a different story. So instead of improve the surface passivation, you have exaggerated surface recombination. So after the anodization, the J0 increased significantly. And if you look at the lifetime data at high injection range, this is after anodization, this is before anodization. At the high injection, is the effective carrier lifetime is dominated by the surface recombination, or the J0. So you can see that you have a reduced effective lifetime, so due to the wrong charge polarity. But if you look at the low injection level, the bulk lifetime starts to play some part, and you can see that you still have an improvement in the bulk lifetime after anodization. And based on Doris' research, it's probably due to the hydrogen passivation provided by this film. So to tackle this problem, where we have increase the surface recombination by passivating the boron emitter, we're trying to use the store charge management. So we're still passivating the same structure, but this time we're using the AO that's formed using a pulse anodization. So at 100%, which means a normal anodization that gives you a positive store charge, you have very high J0 value, but as you reduce the positive cycle percentage, you start to see the improvement in the surface passivation. And in fact, if you are looking at the store charge in figure B, so the black dot are the store charge density. So you start with a very high positive store charge, and it reduces, and you see the improvement in the J0, and at lower positive cycle percentage, you're actually having a almost neutral or negative store charge, and that's where you get your good, better J0. And the interface state in this case is not playing a big part because it's just fluctuate. So about hydrogen passivation. So Doris have done some work on AO incorporation of hydrogen, and she showed that during anodization you actually incorporate hydrogen into the film, and it has the potential to passivate the bulk defects. So this is work that published by Brett. So Brett found that you see this kind of oxygen precipitation ring, and in a lot of literature it is reported that this kind of oxygen precipitation can be passivated by hydrogen, so it can be removed, and most people use firing of this sample with a PCVD silicon nitride, because the silicon nitride stores a high content of hydrogen, and during the firing or annealing, hydrogen would passivate the oxygen precipitation, and this type of ring can be removed. So in my case, I'm still talking about passivating the boron diffused surfaces. So in my case, I see a very similar effect. So that's before, after boron diffusion, before anodization. You can see you have a dark pattern here. This is only a quarter of a 6-inch wafer. So when I'm looking at the whole picture, it's actually a dark ring. So it's quite similar to what Brett observed. So after anodization, so I cut the wafer into a 2-inch segments and still arrange them in the same order. So you can see a quite significant improvement in this part, which is probably due to the hydrogen passivation from the AO. So here's the result that's shown by Doris. So he concluded that after the annealing, you have a very high hydrogen content in your film. So that would help you passivate the bulk defect, or in this case, the oxygen precipitation. All right. Yep, that's almost everything. So I'll give us a brief summary of my key findings here. So first of all, in my early research, I have achieved the localized contact using the self-patterned AO as a template, and we are able to get very good contact with low contact resistance and a reliable device. But the problem is that we have very low cell efficiency due to the very low implied VOC, or the open circuit voltage at the final device. And based on our investigation, it comes from the shallow BSF as well as the long polarity of store charge. So we start to look at a method to manipulate the store charge, and it is demonstrated that the store charge in AO can be manipulated by pulse anodization, and the range that we achieve varies from 2E12 to minus 5E11. And it is also reported in my research that the annealing can have a significant impact on both the store charge and the interface defects. And it is stressed that the oxygen annealing can reduce the oxygen deficiency in your film, and then reduce the positive store charge in the AO stack, which would give your film a better stability. And the forming gas, post-metallization forming gas is most effective in reducing the DIT due to hydrogen passivation. And we also show that AO can provide good passivation on phosphorus diffused surface because it stores a positive charge. But on the other hand, it would give a very high surface recombination velocity for boron diffused surface. And finally, we demonstrate that with the charge management, the surface passivation can be enhanced. Yep, that's basically all my key findings today. So thank you for your attention. And